This class section covers the Cluster Power Controller. The Cluster Power Controller is designed so system software can control power consumption in accordance with the system load. Processing elements can be powered up when needed and powered down when they are no longer needed. The CPC is external to any core and global to the SoC. Access to the CPC can be restricted to one processor or a selected group of processors. The Cluster Power Controller breaks down the coherent processing system into isolated power domains. Domains that can be shut down are indicated in gray. Each processor is in its own power domain, and the coherency manager has its own domain. Each processor domain can be controlled by software through the cluster power control registers. With the shutdown of all 4 cores and an inactive IOCU, the coherency manager becomes inactive and can be shut down also. This slide shows the possible flow between processor states along with some idea of power consumption. The coherent processing system has 4 power states. The processor is in a coherent state when a processor is in a coherent domain. As I covered in the Global Control Register section, the coherent domain is set up by the GCR Core Local Coherence Control Register. In this state, all things on the SoC are available to the processor. The most power is used in this state. A processor is in a non-coherent state when it is not part of a coherent domain. If you have more than one processing element, as is the case for a multi-threaded core, these elements will share an L1 or L2 cache coherently. But as in the case of a single processor, there is no coherent I/O or automatic coherency with uncached memory. The GIC can still be used to map interrupts and communicate through interrupts with another core. This state will use less power than the coherent state. In the clock-off state, the processor will not execute any instructions, but the state of the processor is preserved. Before this state can be entered, the processor must not be part of a coherent domain, and all coherent transactions must be completed. There is significantly less power used in this state when compared to the coherent and non-coherent states. The power down state is just that. The processor is off. The processor state is not preserved. In this state, the processor uses no power. If all the processors on the system are in the clock-off state, the coherency manager, the IOCU manager, and the GIC can also be powered down, leaving only the cluster power controller and possibly external clocks running. The address of the cluster power controller registers must be programmed by the boot code into the GCR CPC base register. This register is located within the Global Configuration Register block. As you can see from the table, only the top 15 bits can be set, so the address is always on a 128K boundary. The CPC EN field controls the enabling of the cluster power controller. Once the boot code configures the cluster power controller, it should enable it by setting this bit. Now I'll show you some code to load the cluster power controller base address into the GCR CPC base address register. First, the base address of the global control register is loaded into A1. Then the base address of the cluster power controller register is loaded into A0. And last, the cluster power controller base address in A0 is stored to the cluster power controller base address register using the offset into the GCR that is stored in A1. A core can control another core's power state by writing the other core's number to the core other addressing register. The core's number goes into the core num field bits 16 through 23. Now I'll show you code to load Core 1 into the CPS Core Other Addressing Register. First, a 1 is loaded into A0 and shifted into position. Then the base address of the cluster power control registers is loaded into A1. And last, the other core's number in A0 is stored to the cluster power controller's Core Other Addressing Register using the offsets of the CPC's Core Local Block and the Core Other Addressing Register. A core controls its power state using the local command register in the local command section of the CPC registers, or controls the power state of another core using the local command register in the other block section of the CPC registers. The only field in this register is a 4-bit command field. The target processor must not be in a coherent domain. If the target processor is in a coherent domain, the command will have no effect until the processor leaves the coherent domain. If the target processor is in a coherent domain, all the cache lines of the processor must first be flushed and invalidated in order to maintain data integrity. Then it can remove itself from the domain by clearing the GCR local coherence control register. Clearing this register disables interventions from other cores and removes the processor from the coherent domain. In addition to this, the OS may require saving of the processor state, especially if the processor is going to be powered down. The clock off command brings the processor from a non-coherent state to a clock off state where nothing is executing in the processor, but the processor state is preserved. The power down command can be done when the processor is in a non-coherent state or a clock off state. The power up command can obviously only be done from another processor writing to the target's command register using the CPC Core Other section. The execution of this command depends on the previous domain power state. If the domain is powered down, a power up command will enable the power for the domain and bring the domain into an operational state of non-coherent execution. However, when bringing the domain up after a power down command is executed, the reset command is generally preferred to a power up. A reset will always ensure a clean start irrespective of the current state. If the previous power domain state was clock off, a power up command will raise the domain state to either non-coherent or coherent operation depending on the GCR local coherence control register settings. The reset command allows a domain in non-coherent operation to be reset. It also can be sent to a domain in a powered down or clock off mode. The domain will then become active and a reset sequence is executed, which leads to the operational state of non-coherent or coherent depending on the GCR local coherence control register. Next, I'll show you the code that will power up a core whose number is in the Core Other Address Register. First, the power up command is loaded into A0. Then the base address of the cluster power control registers is loaded into A1. And last, the power up command that is in A0 is stored in the cluster power controller's other command register using the offsets of the other command block and the command register. With the CPC access register, you can control which processors are allowed to change the CPC registers. The default is for access from any processor. Each processor corresponds to a bit starting at bit 0. Setting a bit enables access for the corresponding processor, and clearing the bit disables access for the corresponding processor.